Hi, my name is Michael Goldfarb. I'm going to talk today about, I guess, some of my experience and perspectives on powered prostheses and also some current work we're doing in semi-powered prostheses. So I'm going to start by just maybe noting that the history of knee prostheses is really one of increasing adaptability, starting in, it's hard to say when it started, let's say the 1920s, you had these single-axis friction knees, pretty basic function. Then in the 60s, started getting much more mechanical complexity, which provided increasing functional variability or adaptability, including explicit swing control and cadence adaptive swing control and explicit stance control. Those were very mechanically complex devices, as you can see. That's a picture on the right of from the mouth patent. So in the 90s, it kind of started replacing that mechanical complexity with mechatronic systems, which enabled eventually more reliable systems with greater adaptability. That trend's consistent with, for example, what you've seen in the automotive industry and other industries over the past 25 years. So the next kind of logical step in that increased adaptability is power prostheses, which, like an MPK, have a microcontroller that can, and obviously number of sensors that can provide greater awareness and much greater control adaptability. But unlike MPKs, the power prostheses have much greater range of adaptability, and they can provide better biomechanics, not just in walking, but across a number of activities. Upslope, downslope walking, upstairs, downstairs, running, cycling, etc. Some of my observations about MPKs are that they have this, kind of much greater capacity to provide biomechanical function, but they also introduce some challenges that are less prevalent in passive MPKs. One is this, what I think of as catch-22 of this range of behaviors they can provide. They can provide a lot more behaviors, a much greater range of behaviors. Those behaviors can be a real asset to people if they're selected at the right time, but they can be a liability if they're selected at the wrong time. And so you need a method to switch between these kind of behaviors in a very reliable and seamless way. Power prostheses also, by their design, tend to be higher output impedance devices relative to passive devices. And increasing the output impedance more or less does a few things, which I'll elaborate on, but it limits the agency of the user, and fundamentally it limits the amount of information that can flow from the user to the device. So then I think if I'm going to identify, I'm going to say three issues. There's kind of a little bit more than that here, but three issues limiting the acceptance right now of power prosthesis on the market. One is that I think users demand complete agency in movement. They have limited tolerance for shared autonomy. They always want to know what a leg's going to do. They always know what a passive leg's going to do. They don't always know what a powered leg's going to do. So that's the one issue, is kind of their, I'd say, demand for complete agency. The other is that catch-22 I mentioned before. If you provide a wide range of behaviors, you need to select between them, and that's also a real challenge right now. And then the last bullet I have maybe a collection of things: size, weight, audible noise, battery overhead relative to passive. There's some tolerance for people to accept increases in those things relative to passive if the first two items and the functionality that's provided by the power prosthesis is worth the trade. But you certainly shouldn't ignore the last bullet. Okay, in working with power prostheses, well, we've also gained an appreciation for some of the things that passive MPKs do well. One is they're generally light and very quiet, and it's compact for the amount of torque they can deliver. The other three bullets I have to do with this low impedance idea. One is that with the low impedance, you have largely a fundamentally coordinated movement between user and device. So I can show that in this video here. This is a passive MPK, and you can see that there's really highly coordinated movement between his body and that device, and that's not, for the most part, artificially controlled through a control system. That's natural and it's fundamental. Uh, the low output impedance also gives him more agency in generating movement. So in other words, the swing's happening for the most part when he wants it to happen, and not before and not after. And also because it's low output impedance, there's this greater potential for implicit communication. So he can provide more movement cues to the device than he could if it were high output impedance. We also, of course, are aware of several deficiencies of MPKs. That low impedance motion we just talked about, it's great when you want the user to convey information to the device, but it also means that environment can, such as when somebody stumbles or scuffs, that the environment would have has a direct line to, or can easily influence, let me say, the movement of the knee. So if you stumble, that foot's going to bounce off whatever you stumble, and it's going to make it harder. It's got bigger perturbation, harder to respond to that. Of course, I'll just go to the last bullet. It's all the movement that I showed in walking is kind of a ballistic movement from double pendulum passive mechanics. If you want non-ballistic movement, you're kind of out of luck for the most part with these. So that leads us to what one of the, I guess, maybe a way to address this problem. I was going to say solution, that's kind of a strong word, but one way that we're addressing this problem is to maybe look at the MPK and say, how can we add power to that to make it better? How can we address the deficiencies in the MPK? And we're doing that with this semi-powered swing assist. Actually, we call it a stance-controlled swing assist knee, but it's basically taking an MPK, like a C-leg, and supplementing it with relatively low power. And by supplementing it with low power, you retain the low impedance and some of the desirable properties, like the quiet operation of the MPK, but you do have power, and with that power, you can at least you can influence swing. And influencing swings gives you, we believe, a lot of value. But first, you can make swing easier for the person, so there's less compensatory action. I'll show some data associated with that. So you can reduce walking effort by assisting swing. You can also help ensure that the knee is fully extended prior to stance, which then is going to, we believe, reduce falls, reduce the likelihood of a fall, rather. Also, as far as perturbation robustness, because we have power, we can react to a perturbation in swing. So when we see a scuff or a stumble, we can inject power and recover the original, or largely recover the original swing phase trajectory, also with the intent of reducing the likelihood of a fall. And then we can produce non-ballistic movement for things like very slow walking, potentially upslope walking, stair ascent, etc. So again, the last point is we can do all this because it's primarily an MPK with some supplemental low torque power. We can do it while maintaining the low output impedance and retain the advantages of low output impedance. So the way our system looks, at least this one, is you basically have this hydraulic system, and you've got a small motor that manipulates or adjusts a valve to so that you can move between low hydraulic resistance, such as you would use for swing, and high hydraulic resistance as you would use for stance knee yielding, either in down slopes, let's say, or downstairs, or very high resistance, such as would be used in maybe a stumble recovery. And then you've also got a swing assist motor, which is a slightly larger motor and then drives the same hydraulic piston through a lead screw. And then at the bottom, you can see basically what that actuator looks like in a solid. This is how that system works when walking. So as I said, the function's basically the same as an MPK. So the hydraulic valve goes to high resistance in stance, low resistance in swing. But what you also have is some pulses of torque and a nominal kind of real-time planned trajectory that helps assist walking during swing. So the user really doesn't have to put in much effort. Actually, this is like one of the first times this user has walked on it. And one thing you can maybe see is he's really putting too much effort into it because he's used to his passive leg. He's later, I think, accommodated a little bit more and understood he doesn't have to work as much with it. So regarding that, we did some experiments with Vicon system and force plates and backing out hip torque and power and compared walking with this in this one subject with Rio knee versus the swing assist. And what you can see here is in red is the swing assist, and in the dashed black is the Rio. And perhaps at the bottom, it's easiest to see. This is averaged over a stride for multiple strides, and you can see the standard deviations there as well. But he got, with the swing assist, a 20% increase in peak knee flexion angle, which we believe increases ground clearance and would reduce the likelihood of a fall, a scuff or a fall. But also we got that increased knee angle with a reduced average hip power and reduced hip torque and hip power. So that's promising with regard to swing assist. The other thing I mentioned is the ability to recover from a scuff or a stumble. So these two are side-by-side videos that show a scuff at the same magnitude of perturbation to the extent that we can control it, and you can see the length of time required to recover. So basically on the right you can see the swing assist, and he recovers pretty much next stride. But with the Rio, it takes him a number of strides to recover because it's just a bigger perturbation because, again, the knee doesn't have the adaptability, the ability to respond and to extend actively. So you can see here, actually, same color scheme. In the red at the top, you have the knee angle versus time. And the red is the swing assist or semi-powered knee, and the black dashed is the Rio. And you can pretty much see the perturbation happens at the same time in both, and the magnitude of perturbation, at least as far as we can tell from the knee angle disturbance, is the same in both. But you get that immediate extension of the knee angle in red in the swing assist, and so pretty much by, I'm going to say, a stride and a half later, he's recovered full amplitude of knee flexion, whereas the Rio, still after several strides, he's sidestepping and not yet recovered into regular movement. And then you can see at the bottom in red is the torque provided by the swing assist. Each stride, again, you get some assistance, but then you can see the stride with the perturbation getting a lot of assistance. Okay, we also can do these what I call non-ballistic motions like stair ascent. So he's getting relatively little assistance in stance. He's able to do stance, with his hip torque, as a lot of people with amputation can. But it's easy for him to go step over because it would normally be a non-ballistic motion. He wouldn't be able to get his foot to clear the stair, but with swing assist he can. So, in summary, as I mentioned, there's the emergence of powered prostheses, which I think is a great and will be a great asset to the market, is consistent with the history of knee prostheses and consistent with the increasing adaptability of knee prostheses. As we all know, these power prostheses greatly increase the range of functionality and adaptability, but bring the challenges of having to select the right behavior at the right time, not yet a solved problem to the level that it needs to be for commercial acceptance. The legs, by their nature, powered legs have more volition, but the control needs to be done such that the person really has full agency and autonomy. So, and then these devices would be helped a lot by lowering their output impedance, which gives a lot more information flow from the user to the person. That can be done in different ways. It's a challenging design problem. You can do it with force sensing and closed loop control, but you have other challenges with that as well. I think there's a lot of room between the strictly passive and fully powered, and that's the room that we've been exploring with semi-powered and hoping to provide functional value while still retaining some of the nice properties of the MPK, such as I mentioned, the user having agency in movement and the fundamental coordination between the movement and the device. That's the end of my talk. Thank you for listening.